Hello everyone. Today I have, a special treat for you, if you will. I'm going to talk a little bit about paleomagnetism and how it works, especially in the deep past. Now, what I have here, I have all my internet open so you can see where I get this stuff. What I have here is a simplified age of the oceanic lithosphere. Why? Well, because that's the best place to get modern paleomagnetic data. Now, what you see here is you see the ages from the left to today, all the way to 280 million years ago. And you can see this is the 280 million year part right here in the Eastern Mediterranean. It might actually be a little slightly older, but other than that, you don't really have anything until about 160. Okay, 170, millions of years ago, because this is what remains of the pre-Pangea crust, ocean floor. That's it, this pink and purple, well, mostly pink, the pink, okay? That's it. Everything else here is Mesozoic or younger, all right? And you see the continents are gray. Well, why are the continents gray? Because they aren't involved in subduction. They are just along for the ride. And you can see the plate boundaries here. There's the plate boundaries, and the continents just move along for the ride. They get to a subduction zone, and eventually they will overrun it, and the subduction zone gets turned off, or a new rift forms, something like that, like you get here. Now, you look at this and you're like, okay, so we could only get paleomagnetic data accurately to about 180 million years. And if you want to talk about pole shifts and magnetic reversals, that's pretty much true. All right. However, nature has given us a beautiful way around this. Now, we don't need another way to reconstruct Pangea. And everybody knows Pangea supercontinent. But there were at least two others before Pangea that we are confident exist. Yes, others have been hypothesized in different arrangements, and it gets messy. And many of you may be familiar with the continent of Ur 3 billion years ago. I guarantee you that thing did not exist. All right, but it's one of those things that just stuck its claws into the public consciousness, even though it basically was one paper. As far as I know, no one has ever tried to confirm or refute that data. So anyway, before I get off on too many tangents, you see this. So Pangea was the first or the most recent supercontinent, and we can get magnetic reversals from that. But there's something you need to know real quick about the magnetic pole. Let me see if I can find it. Oh, it's down here. I'm just showing you this because I want you to see how unstable Earth's magnetic field can be. Most of us know that up until about 700,000 years ago, we've had normal polarity, compasses point north, and we've had a dipole situation like this. However, in that 700,000 years, there have been hiccups, if you will, partial reversals, if you will, or minor flips that flip right back. And this graphically shows you how that dipole can break down. So I'm just going to play it for you. We're looking normal here. The blue is, north, and the red is south. And we have normal magnetic, compass pointing here to the north. And as you get closer here and you start getting towards that 41,000 years, the magnetic field starts to do these wonky things. See, it's becoming more dense over here, less dense over here. Now, Earth is just, here for sake. Doesn't mean that was in Asia. This was in North America. But now look at it. Look at how chaotic that is for a few hundred years. It is not a dipole at this point. All right, look at 41,000. That is not a dipole magnetic field. You see blue here, here. You see south here, here. So red here, here. This compasses would have been wonky 41,000 to 40,000 years ago. Okay, but around 40,000 years ago, it settles back down. That is important to remember because we just tend to think of these things as random flips. You know, one day it's pointing north, the next day it's pointing south. That's not what happens. All right. And Earth's magnetic field right now is not even a perfect dipole. We have the South Atlantic anomaly. Is the Earth trying to flip poles? I don't know. I don't know how long it takes, but based on historic data, to do a full-on flip probably takes at least 1,000 years. Okay. So, and it could take as much as 5. But I don't think the poles are trying to flip right now. It's just probably a normal hiccup. But getting back to paleomagnetic data, and here you can see this is one of the first papers in 2009, I believe it was. Let's go back up to the top so you can see it. Okay. Oh, that's Nuna. Yeah, we'll just use Nuna. Oh, wait, no, let's use this one. Okay, 2009. This is USGS. All right. 2009, as you can see, reconstructing Rodinia by fitting Neoproterozoic continental margins. So we're talking circa 1 billion years ago. And this was in 2009, and this is kind of like the knowledge of the time and kind of kick-started a lot of interest in Precambrian paleomagnetics, okay? Because you can get more than just north or south. Can you use paleomagnetic for dating? Yeah, but it's not really needed for that. It's not really good for that. Usually when you take a paleomagnetic, core anyway, you're going to get a date off of it through zircon. So it's not really something that's used for dating, but it is used for continental reconstruction. And you go down here and you can see this, and you can see 2009, this is what we thought Rodinia looked like. Okay, you can see 900 to 1200 million years ago. But this has changed somewhat. We do know now Rodinia was never just one Pangea type thing. And the Pangea even wasn't all land masses. I think it was about 88%. And that seems to be as much as it's ever been. Now, if you were to construct it, what time is it? Is it closer to 900, 1200 million years ago? I don't know. But it was more of a glance, I don't want to put this, sort of a merge and split supercontinent. Like you had a core, which does, and I'm not being biased here, but it does appear to be Laurentia, which is North America. Okay, that's what it seems like now. And it seems like Amazonia was a key part of it as well, South America. So you basically had North America and South America, and you get these glancing, things would merge and glance off, and then something else would come in. That's kind of what it was really like. So the supercontinent persisted for a lot longer, if you will, than Pangea, but it's just because it was still rearranging itself. It was not as stable as Pangea. Okay, so why that is, I don't know. But how do we even know this? How can we even gauge anything like this? Well, this is somebody I know personally, and when she was doing her doctorate at Tech, I would go out with her and drill cores for paleomagnetic data, and now she's stuck in Iceland. Oh, whoa, how terrible. But in 2015, she did her dissertation, and it was actually really good. And I don't want to show it here, but you can get it from Michigan Tech if you would like. It is downloadable. You know what? And by the way, she's not Icelandic, she's Finnish, actually from Finland. So, yeah, and then she ended up in the Upper Peninsula, and Michigan Tech. Yeah, this is it. And yeah, accept all cookies. I do have a copy of this, but my hard drive's not connected right now. Oh, you're gonna make me do this. Well, anyway, I'm not gonna hook up my hard drive to show it to you, but I think I may have shown it to you guys before. But if you can, dissertation, it's a dissertation, it was a PhD, so you can go there and look. All right, now, how do we get that? We don't have ocean crust. See, we have ocean crust going back to 300 million-ish years ago. Well, the Neoproterozoic, Rodinia, was about 1 billion years ago. So how do we reconstruct that? Well, thankfully, we have these things called large igneous provinces, or lips. And this is a paper, conjoined paper, that several people did, and you can read this if you want. It is a good paper. Okay, I just wanted to show you that because it's very technical, but it takes you through a lot of the processes and walks you through a lot of this stuff, and that's good. Okay, so basically, you get these igneous intrusions within the continent, and like the ocean crust, they'll be mafic, and they will record the north, where the polar north was, and even about latitude. You can get latitude too from these reconstructions, and I'll show you a paper about that. But that's how we do it, okay? So, and this is Nuna. This is circa 1.4 billion years ago. And this one, how old is this paper? Does this version not have 2010? Okay. And you look at Nuna here, and this is kind of just like, well, maybe this was it. This is completely incorrect. Nuna, being about 500 million years-ish older than Rodinia, is a lot harder to reconstruct. Not because we don't have large igneous provinces, it's because of metamorphism. The further back you go, the more metamorphic rocks tend to be. Even if they are basically igneous, there'll be some sort of metamorphic event, minor resetting. And it's hard to pick that out a lot of times. And the closer you are to today, the less likely that is to happen, and the easier they are to pick out, because there might just be one or two. But you start going back and you get problems. This is why anything past Nuna, like anything about Kennerland or Ur or anything like that, is basically guesswork at this point. We may have had supercontinents that 2.5 billion years ago and older, or we may not have, okay? And that's it. Maybe 2 billion years ago we probably did, but we just haven't been able to reconstruct that stuff yet. And we may never be able to really accurately do it, okay? And this hasn't improved much. I think, if I remember correctly off the top of my head, here's Grenville. That's basically Nova Scotia down to like Georgia, okay, essentially. It's this little strip here. And here you can see Superior. And here you can see it's attached. Now, Grenville's complex. It's basically the Grenville set of orogenies, because it's really several, and within a couple 100 million years. The eventual Appalachians would form in that same area. So this whole thing is just this complex set of orogenies of rifts and assemblies and rifts and assemblies that are really hard to work out as well. But I'm going to show you, close that, Rodinia. I'm going to show you this for the Jacobsville Formation. We now know the Jacobsville, this is 2024. The Jacobsville is a group now. I redefined it back in 2014, I think it was. But anyway, besides the point. The Jacobsville is a sandstone, and this is a study area. The Jacobsville, Bayfield Group and Jacobsville are, I believe through my investigations in the field, they are congruent, they do correlate. The reason why people haven't correlated them is because of the big Keweenaw Fault here. You see the Bayfield Group can be divided out easily here, and it does continue over here, but it changes lithology. You get one of those facies changes. The middle pure unit on this side, the west side of the fault in the Bayfield, is called the Devil's Island, and it's a quartz arenite. Most of the sands in the Keweenaw Rift that filled in the sands when that rift failed are not quartz aranites. They're arcosic, or they contain lithic bits. It's one of the rare places on Earth where you're not going to run into tons of quartz sandstones. But over here, that layer does exist. It just thins out and eventually probably peters out before Marquette. Okay? But it is there. Limestone Mountain's this little anomaly. I'm not going to talk about that. We think that might be a detachment block. There are some of the old school geologists who think it's a kimberlite, but it can't be the way it's set up. But anyway, I digress. So you see the fault here, and you have these red volcanics here. They're colored red here. That's the mid-continent rift rocks, okay? And Agate Falls is down here. This actually is an isolated area of the Jacobsville. It's just you don't see it on this map. These faults, oh yeah, the Owen and the Douglas are up here, that's why. Now, you see you have all these igneous rocks, and this is the Copper Harbor Formation's the brown. Okay, I redefined that in 2016. People actually do use that one. Okay, and I'm going to show you the reason why I'm bringing that up before I show you this reconstruction is this is on ResearchGate. This will eventually appear in papers. I'm still working on my Frida, and I am still working on my oh crap, what is that igneous intrusion called? You'll see it here in a minute. But this is there for now. This is it has been looked over, but basically the point of me doing this is I hate doing statistical stuff. I really hate it. But I need to do it in order to set a time frame and see if hypotheses work. Okay? Well, that's another thing. These detrital zircon ages in the Jacobsville are pretty similar to the Bayfield groups. And you see here's the Devil's Island Formation. It kind of just peters out. Anyway, so what you're looking at here is this is basically west and east. Basically this transit line. Obviously you have tons of vertical exaggeration in the thousands. Okay? But here you have an unconformity. Here's your Keweenaw Fault. That's what upset it. So this is what people used to call the Jacobsville. This is what they used to call the Bayfield group. I just made it all Jacobsville because this name came first, and I pulled the formations over. So now it's one thing. You can see you have around the Jacobsville. And the Jacobsville, these are the youngest dates in the Jacobsville. So our Jacobsville, Bayfield group, whatever you want to call it, was deposited at least in 992 million years ago, maybe a little younger. Because remember, you can be younger than this, you just can't be older. But it's probably around this time because that's about the time the Keweenaw Fault formed. So maybe 950-ish. I mean, the Keweenaw Fault was probably activated multiple times. Okay? Now, we are still, so we have 933. This is as old as it can be, and that makes it Neoproterozoic, okay? Because these are detrital zircon dates. These are not igneous dates. Oh, yeah, the Bear Lake rhyolite. I tried dating this thing again. Fail. But I was able to delineate it a lot better, okay? So you can see these are detrital dates here. This is a direct date. You see, we get this wonky stuff. And it's not a rhyolite. It's actually a latite. And we can just call it the Bear Lake stock. This thing has so many names, but it's Bear Lake. That's why one of my papers coming up is just going to be making that a member of the Frida Formation. This pink thing's the Frida. Okay? And we have one detrital-ish from there. We have several detritals from the Nonsuch. Okay? And then we get into the Copper Harbor. And you can see these greens. These greens are all igneous. These are the mid-continent rift rocks. And you can see that they have been dated. We know the dates. So you get, and this one, Hunter's Point flow, has been dated. So anything between here and here, sedimentary-wise, we know is between these two dates. Okay? This 1087's probably more accurate. For Hunter's Point is actually probably a couple of flows, but that's the oldest. So all of this, the Gorge Falls member, the Great Conglomerate Falls, half of the Sandstone Falls member are all between 1094 million and 1087 million years ago. Okay? So we got that. Now we could drill into these, since we know these were surface flows. We could use dikes as well. But we use these, we drill in them, and we can get paleomagnetic north. And we usually use things like this. You see all these dike swarms. They all have names. This is Superior Craton. This zone, I forget exactly its significance. But you look at this and you see that the time frames have been dated-ish. So you would go to one of these dikes, you take a adapted chainsaw, essentially, with a coring barrel on it that's about 1 inch. It's actually 2.5 centimeters, but you drill in, you take your sample maybe an inch, inch and a half deep. And then you take your adapted brunt and compass so you can get its orientation, because you need that, and you mark it, and then you take it back to the lab and you run it in. You just let it do its thing, okay? And it'll give you a date, and it'll give you an approximate paleo latitude, okay? So that's how we do this on things this old. So see, we just use continental stuff. So let's see when here. All right, we don't need this anymore, but you can look at this if you want. And these dates, the hypothesis is that I'm working on is that I think the Frida is right near the Mesoproterozoic, Neoproterozoic line. It's a very thick formation. It does intertongue with the Nonsuch, so it could have been deposited. It could have spent 70 million years being deposited, but I may be wrong too. You get 1123 down here, which is pre any of this. So maybe it was closer. Anyway, I digress. But see, you can see the dates here. False formation, and here's the sources. And here's just basically a strat column that I've used in a lot of my videos. Okay, so we're going to close that now because I don't think we need that. We are going to come down here, and you see these are stereo net projections, okay? And you can see you have normal polarity and reverse. And the fact that we can reproduce this data tells us that Earth's bipole essentially goes back at least slightly more than 1 billion years. Actually, it's probably more like 3. But we did have a dipole, okay? Because you would not be able to produce what I'm about to show you if you didn't. Now, when you go this far back, if reversals actually do take 1,000, 2,000 years, that flip isn't going to show up. You'll see, matter of fact, there's one little mountain in the Upper Peninsula. There's 2 dikes that crisscross each other, and they're both Keweenaw. One's normal polarity, one's reversed, but they're almost the same age. So within that narrow span of, I think it's like 40,000, 50,000 years between the deposition of those two, the poles flipped. Okay, and I just think that kind of stuff's really interesting. But anyway, then you take this data. This is a best fit line, essentially. Okay, and fit results, normal bell curve. I'm not going to go too deep into you at this because it is technical. And Lisa knows far more about this than I do. I'm more of the, geophysical guy. But anyway, you come down here and you can produce a map like this. And this is about the Jacobsville deposition. And you form a track. This is just a track. This is how Laurentia in the area, the Superior Craton essentially, moved from 1,109 million years ago to about 990 million years ago. These were meetups, okay? So we're basically in this time frame constructing Rodinia is what we're doing. And you can see the errors, the bubbles are the errors. Because you're working with stuff that's 1 billion years old, you're gonna get resets and stuff like that. So you try to average the best you can. Some margins of error are really small, okay? Now, could this is a nice smooth curve, but could this have gone like this and come like this? Of course. That it doesn't mean it couldn't have. But you see this, and this is just extrapolated because this comes in and then we know we re-met up with Grenville. That does not mean Grenville is part of Australia. The position of the continents are just to show you the modern spread of the continents. Okay, Grenville is the eastern seaboard of North America, essentially. Okay, up from Nova Scotia down to Georgia, all right? So this is our Keweenaw track. And by the time the Frida and the Jacobsville get deposited, we're down here somewhere. All right. And here's the age in millions of years. So the Frida is probably in here. I mean, I would be stoked if it was closer to the billion mark, but I don't think it is. And you can see the Jacobsville's in red. Why? Because there's an unconformity there. And so you see, so this is basically the Jacobsville, the North Pole, okay? We wouldn't be able to do this if we did not have a bipole or dipole situation on Earth. This would not work. And the fact that it does tells us we have dipole. So this would have been North Pole for the Jacobsville circa 990 million years ago. And this is how Laurentia, North America, moved. And here's where it meets Grenville, Amazonia, Kalahari, part of the bottom half of Africa, Baltica, that's the Scandinavian part, and a little bit of Germany and Estonia, Latvia. Anyway, okay, and this is how we think North America sat. Now, position implied by Halliburton pole, you can read up on that if you want, but this is likely correct. So the Jacobsville was deposited down here, okay? So we're south of the equator at this point, which is funny because about 500 million years later, North America would be almost in the same position again, except it would be up here a little bit closer to the equator and a little more rotated counterclockwise. But anyway, that's during the Cambrian. Anyway, I digress. So you see, this is basically how it moved from the beginning of the Mid-Continent Rift until the end. All right? So this is why we do this. Okay? And you may be like, well, these dates, you get them from the Jacobsville. No, you don't. Like I said, you can't directly date sedimentary rock. All right? But there's so many intrusions in this stuff that if you can date the intrusions, you can get paleomag data, you got dates. That's the beauty of the Mid-Continent Rift. Okay? And that paper is, here you can see that. All right, let's close that. What else we got here? ResearchGate. We got that. So, yeah, so even though these areas are gray, we could still pull data from them. I thought I closed Elisa. Yes, I didn't. So now we're back to Rodinia. And I want to show you, let's see, Galganda, East Galganda, Cratons on a Pangea base. Okay, what is this? I wanted to talk about this actually. Excuse me. All right, this is essentially Pangea. Now, Cratons are a key part of determining whether or not something is a continent. No Craton, no continent. Now, most of us don't consider this Cratonic. It's too young. I mean, it's not really a core of anything. But you can see it's mostly, they're all Precambrian and mostly are Proterozoic because Proterozoic's the largest chunk of time. And these are all Proterozoic in this case. There are Archean ones and they fall within these. And then your Proterozoic, your Archean ones are kind of like the nuclei that the Proterozoic ones formed around. You can see there's lots of Cratons. And you can see there's lots of Cratonic development or continental crust being created around 2 billion years ago. So there probably was another supercontinent around that time. We just don't know what it was. There are people who have proposed them. It's probably more like 1.9 billion, but anyway. And these are other reconstructions. As you can see, back in 2009, we really didn't have a firm grasp on this, and paleomagnetism had yet to really be thoroughly done. It has been doing done since the 70s. It has been done since the 70s on the area. But this actually, 1998, Wheel and others, Wheel had it the closest. Here is Laurentia, here's Amazonia, here's Baltica, Greenland. We are pretty confident of this. This would have been your core. Everything else would have been glancing off, okay? This is as close to as good as it gets, all right? I was looking for a non-pay paper to show you. Yeah, see, here is Hoffman, based off Wheels, and this is pretty close. And these are the belts. What is that? That's your orogenies. That's your mountain. Like today, you have mountain belts. During Rodinia, it was basically circumglobal, okay, at one stage. So, and here you have poles. Here you have your paleomagnetic poles. So your polar wander, you have your positions. Sorry, not paleomagnetic poles. You have your paleomagnetic data, your wander here. In green, that would be Laurentia. And as you can see, it's still pretty consistent with the modern numbers, except the margins of error on this were huge then in the early aughts. And this reconstruction is not really the best, but anyway, once you get out of this, is you see Laurentia in North America, and you see that even in 2009, we still had a decent understanding, and we still have the Frida would have been down, or the Jacobsville would have been down here, and Laurentia would have been down here 990 million years ago, okay? And this is a typo here. There should be another 1 in here, but that happens. And this, see how messy this can get? This is why this is not easy to do. And this is in the early days where the margins of error were huge. The data was limited. And what data you did have was basically in, areas of great study like Africa, okay? This would have been the middle Congo, Southern Africa, what we call Sahara, okay? So this is basically Africa on its side, rotated 100-odd degrees clockwise. This is Amazonia, this is Baltica. Okay, here's Greenland. Greenland, until recently, has basically always been a part of North America since as far as we can tell, okay? And Siberia is the purple. This is not correct. We know that now. So these would have been, the study went in Antarctica. We were still using data from the 80s, 70s and 80s at this point. And here's Antarctica. All right, so Antarctica, according to this, was at the equator. But like I said, this reconstruction is not the best. But, that's how we learn. We move on. And here's 850 to 670. So this is the Neoproterozoic. This is getting near the Cambrian. Okay, and you can see how things have changed. The past, you can see we have Laurentia near the South Pole now. Rodiania's history, and 850 million years ago is the oldest Grenville intrusion we have. Or the youngest, it's not the oldest, it's the youngest. So, so this is just interesting. This takes you up to the Cambrian, okay? And just for you to look at, you can see the colors here, all right? So I just thought that this would be an interesting thing to show you, because we don't usually, when we think of, oh, there's my guy. When we think of paleomagnetism, we tend to think of how it relates to Pangea or Younger or the modern ocean floor. And this was just an introduction for me to show you how it goes far, far, far past that. Okay, I think that's it. If you have any questions or comments, please leave them below, and I hope you learned something.